Picture this. You're standing at Cape Canaveral, watching humanity's most advanced rocket, a SpaceX Starship, thunder into the sky. Its 33 Raptor engines generate the power of 16 million horses. Yet this marvel of engineering will still take 9 agonizing months to deliver astronauts to Mars. Your great-grandchildren might live to see humans on Saturn's moons. Maybe. Now imagine standing at that same launch pad in 1965, watching a spacecraft the size of a battleship rise on pillars of atomic fire. Each explosion, a controlled nuclear detonation, hurls this 4,000-ton colossus higher, faster, until it's racing through space at velocities that make our best rockets look like horse-drawn carriages. Mars in 125 days. Jupiter in a year. The entire solar system opened within a human lifetime. This wasn't science fiction. This was Project Orion. Between 1958 and 1965, America's brightest minds at General Atomics, backed by the Air Force, DARPA, and NASA, designed, tested, and proved we could surf nuclear explosions to the stars. The mathematics were elegant. 2,000 to 6,000 seconds of specific impulse, 10 times better than any chemical rocket ever built. We had working prototypes. We had the nuclear devices. We had Freeman Dyson's calculations showing we could reach 11% of light speed. And then, in a supreme act of cosmic self-sabotage, we signed it all away. The Partial Nuclear Test Ban Treaty of 1963 didn't just end atmospheric nuclear testing. It murdered humanity's best chance to become an interplanetary species before the century's end. The story begins not with a eureka moment, but with a puzzle that haunted physicists through the dawn of the atomic age. In 1946, Stanislaw Ulam, the mathematical genius who would later help design the hydrogen bomb, scribbled an equation that would change everything. What if, instead of trying to contain nuclear explosions, we rode them? Think of it this way. Every chemical rocket is fundamentally a controlled explosion pointed downward. We burn fuel, create expanding gas, and Newton's third law does the rest. But chemical reactions release energy like striking a match, while nuclear reactions release energy like detonating a star. The energy density difference isn't just significant. It's the difference between crawling and teleporting. The breakthrough came during Operation Teapot in 1955. In the Nevada desert, where the sand had been turned to glass by previous atomic tests, scientists arranged basketball-sized spheres at various distances from ground zero, some naked steel, others coated in graphite. The prediction was total annihilation. The result defied every expectation. When the 14-kiloton blast wave hit, a wall of plasma hotter than the sun's surface moving at 100 kilometers per second, something miraculous happened. The graphite coating on certain spheres didn't just melt or burn, it sublimated instantly, jumping straight from solid to gas in microseconds. This created what physicists call an ablative shield, a bubble of expanding gas that pushed the main blast wave away from the sphere's surface. Like a silk scarf protecting your hand as you pass it quickly through a candle flame, the vaporizing graphite saved the steel beneath. But here's where it gets cosmic. These spheres didn't just survive, they flew. The asymmetric ablation on one side created thrust. Nature had just demonstrated the principle of nuclear pulse propulsion, and Lou Allen was there to witness it. By winter 1957, Ted Taylor at Los Alamos, a man who could design nuclear weapons the way Mozart composed symphonies, joined forces with Freeman Dyson at General Atomics. Dyson, taking sabbatical from Princeton, brought the mathematical rigor of theoretical physics. Taylor brought the practical knowledge of nuclear explosives. Together, they calculated something extraordinary. A properly designed plate could capture 85% of a nuclear blast's momentum while surviving thousands of detonations. The physics were undeniable. If you detonated a 1-kiloton device 60 feet behind a massive steel plate coated with oil, the oil would vaporize into a plasma jet. This jet, expanding at tens of kilometers per second, would strike the plate like a giant's palm, delivering a crisp 30 meters per second of velocity change. String these explosions together. Boom, boom, boom. And you're not just reaching orbit. You're reaching relativistic velocities. To understand the audacity of Project Orion's engineering, imagine you're tasked with building a ship that must survive being repeatedly kicked by nuclear bombs, smooth those kicks into comfortable acceleration, and do it all while carrying enough atomic fuel to tour the solar system. Oh, and the crew needs to survive. The spacecraft they designed was a monument to controlled insanity. Picture the Empire State Building laid on its side, made of steel, and fitted with the universe's most violent engine. At 80 meters tall and 40 meters wide, Orion would have dwarfed every spacecraft we've built since. The International Space Station could fit inside its cargo bay. At Orion's heart lay 4 engineering miracles, each solving an impossible problem. The pusher plate. Imagine a steel disc the size of a baseball diamond, 4 meters thick at the center, tapering to knife edges. This wasn't just armor. It was a momentum transfer device that would face nuclear hellfire every 3 seconds and ask for more. The secret was its coating. A thin layer of oil or plastic that would vaporize with each blast, carrying away heat while the steel beneath remained cool. Like a boxer's glove distributing the punch, the plate would spread each nuclear hammer blow across its entire surface. Nuclear pulse units. These weren't crude atom bombs, but precision-engineered propulsion charges. Each unit, about the size of a hat box, contained a tiny nuclear device wrapped in a tungsten casing. When detonated, the tungsten would vaporize into a directed plasma jet, focused like a shaped charge toward the pusher plate. During launch, these 0.1 kiloton units would detonate every second. Once in space, larger 20 kiloton units would fire every few seconds. The ship would carry 800 of them in revolving magazines, like bullets in the Devil's Own machine gun. The shock absorption system. This was the magic that transformed nuclear violence into smooth acceleration. Picture a 2-stage system. First, massive toroidal gas bags, like enormous steel donuts filled with helium directly behind the pusher plate. These would compress with each blast, absorbing the initial spike. Behind them, 4 telescoping pistons, each the size of a subway car, connected the pusher to the main spacecraft. Together, they transformed the sharp kick of each explosion into a steady 1.25 grams push, about what you'd feel in a sports car accelerating hard. Astronauts could walk around during thrust, sipping coffee while nuclear bombs exploded beneath their feet. The pulse delivery system. Essentially a nuclear bomb vending machine. Every 3 seconds, a mechanical arm would grab a pulse unit from the magazine, slide it down a launch tube, and fire it through a hole in the pusher plate. The bomb would travel 60 feet behind the ship, detonate, and the cycle would repeat. The precision required was extraordinary. Mistiming by even a fraction of a second could destroy the ship. In November 1959, they built a proof of concept called Hot Rod, a 1-meter model powered by conventional explosives. In a field in California, this tiny prototype rode 6 sequential blasts up to 100 meters, proving the impossible. You really could fly by setting off bombs under your spacecraft. The engineers celebrated with champagne while the model's parachute brought it safely back to Earth. Freeman Dyson ran the numbers obsessively. An atomic-powered Orion could achieve velocities of 3 to 5% of light speed. Replace the fission units with fusion bombs, and you could hit 10%. At those speeds, Alpha Centauri, our nearest star, transforms from an impossible dream to a 40-year journey. Within a single human lifetime, we could touch another sun. Every great tragedy needs its villains, but Orion's death came from something worse than malice. It died from fear, bureaucracy, and humanity's inability to see past its own shadow. NASA, created in 1958 as a civilian agency born from Cold War paranoia, wanted nothing to do with nuclear weapons. The agency's administrators, trying to sell space exploration to Congress and the American public, had chosen the moon as their target, and chemical rockets as their steeds. Apollo was safe, photogenic, and politically palatable. Orion was none of these things. As one NASA official reportedly said, "We're trying to send American heroes to the moon, not nuclear bombers to Mars." The Air Force saw different possibilities, darker ones. In 1959, when they took over Orion's funding, generals began sketching plans that would have made Dr. Strangelove proud. Orbital battle platforms carrying nuclear weapons, doomsday Orions that could rain atomic death from space, deep space interceptors that could hunt enemy satellites throughout the solar system. One classified study proposed a 10,000-ton Super Orion that could carry 500 nuclear warheads to any point in the solar system. The scientists who dreamed of exploring Saturn's rings watched in horror as their Starship became a weapon. Meanwhile, the public was learning what atmospheric nuclear testing really meant. By 1963, strontium-90 from bomb tests was showing up in children's teeth. Every thunderstorm brought radioactive rain. The Limited Test Ban Treaty, signed on August 5, 1963 by Kennedy, Khrushchev, and Macmillan, banned nuclear explosions in the atmosphere, underwater, and in outer space. It was a treaty born from humanity's first glimpse of planetary-scale self-destruction. For Orion, it was a death sentence written in diplomatic ink. The treaty went into effect October 10, 1963, and suddenly, the most promising propulsion system ever developed became illegal under international law. NASA quietly withdrew its support. The Air Force, denied their orbital weapons platform, lost interest. By 1964, Project Orion was officially canceled, having spent just $11 million over 7 years, less than the cost of a single Saturn V launch. Freeman Dyson would later write with barely controlled fury, "This is the first time in modern history that a major expansion of human technology has been suppressed for political reasons." He calculated that if Orion had been developed instead of Apollo, we could have established a 100-person Mars base by 1985 for the same cost as landing 2 men on the moon. Ted Taylor, watching his life's work cremated by bureaucracy, made one last attempt. He proposed launching Orion from the moon or from deep space, avoiding the treaty restrictions. Nobody listened. The man who had shown humanity how to ride nuclear explosions to the stars spent his last years advocating for nuclear disarmament. His dreams of interplanetary civilization buried beneath the weight of what might have been. But physics doesn't forget. The equations that made Orion possible still whisper from textbooks, waiting for humanity to remember its courage. In June 2000, at a small aerospace company called Andrews Space, a team of engineers decided to resurrect the dream, but with a 21st century twist that would sidestep every political landmine that killed the original. Mini-Mag Orion is nuclear pulse propulsion reborn for the age of magnetic confinement. Instead of nuclear bombs, picture fuel pellets smaller than aspirin tablets, each containing less than 100 grams of fissile material. Instead of chemical explosives, imagine magnetic fields powerful enough to crush atoms. It's the difference between using dynamite and using a precision laser. Same physical principle, radically different execution. Here's how it works. A pellet of uranium-235 or plutonium wrapped in a shell of conducting material gets injected into a magnetic compression chamber.
2.
Capacitor banks carrying the energy of a lightning bolt dump their charge in microseconds, creating a magnetic field so intense it could levitate a freight train. This field crushes the pellet in what physicists call a Z-pitch. Imagine an invisible fist squeezing the pellet from all directions simultaneously.
Scooter, no action.
The compression triggers fission, but in a controlled, confined manner. No mushroom cloud, no fallout, just pure directed thrust. The innovation is breathtaking in its elegance. magnetic nozzles, essentially electromagnetic fields shaped like invisible rocket bells, capture and direct the expanding plasma.
Atlantis on its way, all
Even
three
better,
engines now
they can
throttling
recapture
down
part
as
of the
area
energy
begins
from
as
each
the
pulse
vehicle
to charge
passes
the
through the area of
capacitors for the
maximum
next
dynamic
one.
pressure.
It's nuclear propulsion that powers itself, each explosion making the next one easier. Andrews Space, working with Sandia National Laboratories' Z machine, a magnetic pulse generator the size of a warehouse, demonstrated that the physics worked. They showed that mylar films could direct current into fuel pellets, creating the imploding magnetic fields needed for compression. The results were everything they hoped. Specific impulse exceeding 10,000 seconds, thrust comparable to the Space Shuttle main engine, and efficiency that makes chemical rockets look like burning coal in the age of fusion. The performance numbers read like science fiction: 100 tons to Mars in 3 months, Jupiter in 1 year, a crewed mission to Neptune, in less than 5 years. With Mini-Mag Orion, the entire solar system becomes as accessible as low Earth orbit is today. Yet here we are in 2025, and Mini-Mag Orion remains a paper spacecraft, unfunded and unbuilt. The tragedy isn't technical. Every component has been demonstrated. It isn't even political. No treaties ban magnetic confinement fusion in space. The tragedy is one of imagination. We've become so accustomed to the slow boats of chemical propulsion that we've forgotten to demand the starships physics says we could build. Step outside tonight and look at Mars. That red point of light that has captivated humanity since we first looked up. With our best current technology, astronauts heading there will watch Earth shrink to a point of light over 9 months of travel, aging a year for a round trip, facing radiation, muscle atrophy, and the psychological toll of extreme isolation. Now imagine a different timeline, one where courage trumped fear in 1965, where Freeman Dyson's Orion rose on nuclear fire from the Nevada desert, carrying not weapons but scientists, not warheads but greenhouses. By 1970, nuclear pulse ships would be ferrying colonists to Mars in 10-week luxury cruises. By 1980, we'd have research stations on Jupiter's moons. By 1990, human beings would be standing beneath the rings of Saturn, looking back at Earth as a pale blue dot not through robotic eyes, but through the visors of their helmets. We had this future in our hands. The blueprints still exist, archived in filing cabinets at NASA and Los Alamos. Dyson's calculations, showing we could reach 11% of light speed with fusion pulse propulsion, remain as valid today as when he scribbled them in 1958. The hot rod test footage, showing that tiny model riding explosion after explosion into the California sky, proves it wasn't fantasy. We chose to abandon this technology not because it didn't work, but because we were afraid of what it meant. Afraid of the nuclear genie. Afraid of militarization. Afraid of taking the giant leap that physics offered us. Every Mars mission delayed. Every probe that takes decades to reach the outer planets. Every astronaut who spends a year of their life traveling to our nearest planetary neighbor. They're all monuments to our self-imposed limitations. We're like sailors who discovered steam engines but chose to keep using wind, afraid the boilers might explode. The question for our generation isn't whether nuclear pulse propulsion works. We proved it does with slide rules and vacuum tubes. The question is whether we'll ever again possess the combination of vision, courage, and desperation that made the Apollo program possible. Because out there, beyond Earth's magnetosphere where treaties don't apply and fallout doesn't matter, the physics that could carry us to the stars in years instead of centuries is still waiting. Mini-Mag Orion could be built with today's technology for less than the cost of a single Mars mission using chemical rockets. But it sits unfunded while we continue to accept the tyranny of the rocket equation, prisoners of our own timidity. Perhaps what we need isn't better technology, but better dreams. Dreams big enough to make us reconsider the calculated risks of nuclear propulsion against the certain stagnation of remaining Earthbound. Dreams that remind us that every moment we delay, the stars grow older. And so do we. Tell us, would you board a nuclear pulse spacecraft knowing the risks if it meant seeing Saturn's rings with your own eyes? Or have we made the right choice, keeping this atomic genie locked away while we inch across the cosmos on chemical flames? Is safety worth the stars? Because somewhere in an alternate universe, there's a version of humanity that said yes to Orion. And tonight, while we look up at Mars through telescopes, they're looking down at it through windows. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.